Welcome back, everyone, to Flight Vehicle Dynamics. This is lecture 32 in week number 13. So let's continue the talk about the lateral directional static stability. And last time we saw the conditions for the lateral static stability. So today we have to cover the directional static stability. Remember, the directional motion is the motion that happens in the XY plane. So it's a synonym with the yawing motion of the aircraft. And in fact, the moment that is associated with the directional stability is the yawing moment, N, which as usual can be written as a product of the yawing moment coefficient Cn, the dynamic pressure, the surface of the wing, and the wingspan. As usual, the coefficient is a function of various variable, such as the side slip angle, the aileron deflection, the rudder deflection, Mach number, Reynolds number, angle of attack, and location of the center of gravity of the airplane. Now, if we fix the latter four, so Mach number, Reynolds number, angle of attack, and location of the center of gravity of the airplane, then Cn reduces as a function of beta, delta A, and delta R, linearizing it about the 0, point. We have our usual expression with a bunch of derivatives, and the coefficient Cn0 evaluated at beta equals to delta A equals to delta R equals to 0. Like we saw for the side force coefficient and for the rolling moment coefficient, also the yawing moment coefficient Cn0 is 0 for symmetrical aircraft unless we're considering exceptional cases in which a particular aircraft has a long, slender nose and at high angles of attack, asymmetrical vortices start to shed from the nose, so that Cn0 would not be 0. But for most cases, Cn0 is 0. Now, the first derivative that we encounter that is non-zero is Cn beta. So the change in terms of the yawing moment due to a non-zero or a change in the side slip angle beta. And this is the directional static stability derivative. So the sign of this derivative determines whether or not the aircraft is stable in terms of the directional motion. So sometimes this derivative is known as the weathercock or weather vane stability derivative. And here we have a weather vane. And the condition for this stability to hold is that this coefficient, this derivative, Cn beta, has to be positive. And this is, in my opinion, a little bit easier to understand than the derivative for the lateral stability. So let's see why this derivative has to be positive. So let's consider an airplane, like in this drawing over here, with a positive side slip angle beta. So we have the wind that is pushing on the right side of the airplane. And in order to cancel out or reduce the side slip, we need the airplane to react so that it produces a positive yawing moment. And that is the condition so that there is stability. If the airplane would produce a moment on the other side, so a negative yawing moment, then the side slip angle would increase instead of decreasing. And so the directional motion would be unstable. But in case of a directionally statically stable aircraft, well, the aircraft will tend to align in the direction of the relative wind, exactly what happens with the weather vane. And this is done by having a vertical tail. In fact, the vertical tail is the primary aircraft component that contributes towards the value of the derivative Cn beta. In fact, you can think about the air pushing on the vertical tail and producing this yawing moment so that the airplane turns in the direction of the relative wind. Now, if we analyze the composition of the derivative, well, we should have, to be precise, two contributions, one given by the vertical tail and the other component given by the wings and the fuselage, so WF. Most of the times we can just in first approximation, since the contribution of the vertical tail is much higher than the contribution of the wings and the fuselage, we can approximate Cn beta as completely equal to Cn beta of the vertical tail. In terms of the magnitude of Cn beta, well, the larger the tail surface is and the further the tail aerodynamic center is from the aircraft center of gravity, the larger the derivative Cn beta is. And in fact, we can write Cn beta, at least the component due to the vertical tail, as the component Cy beta of the vertical tail that we saw last time times a length xv. Now the length here is non-dimensionalized using the wingspan, but this xv is the length between the center of gravity and the aerodynamic center of the tail. So for the rolling moment we saw last time, the length, the reference length to calculate the moment was zv. And in this case, we have the length, since we're referring to the yawing moment, we need the x direction, so xv. And it is positive, it is considered positive if the aerodynamic center, or the center at which the side force is applied, is behind the center of gravity. So it has to be a tail, okay, the back of the aircraft. If you had the tail in the front, well, it wouldn't be a tail anymore, but let's say if you had a surface on the front, then xv would be negative and it will create instability. Just a consideration of the contribution due to the wings and the fuselage. Well, we have for aft wing sweep, so for wings that are swept backwards, the contribution is positive, and this is because, so this is the same drawing that we saw last time. If we had a relative velocity, wind velocity v infinity, with a certain angle, so in this case we have a positive side slip angle, then there's more normal component of this relative velocity hitting the right wing with respect to the left wing. You see that this v perpendicular for the right wing is larger than the v perpendicular for the left wing. So this creates more lift on the right wing than for the left wing, but more lift means more induced drag. the drag induced by the lift itself. So since we have more drag on the right side than on the left side, then a positive yawing moment is created. So for positive beta, the fact that the wings are swept backwards creates a positive yawing moment. So Cn beta, due to the wings swept backwards, is positive. Of course, all these sets of coefficients, as I said in the beginning, are determined for a specific combination of Mach number, Reynolds number, and especially angles of attack. So the analysis that I've described so far is valid for usually low angles of attack. But for high angles of attack, well, the derivative might be negative, so we might lose the directional stability. And you can take a look at figure 5.30 in the book. It just gives, let me just summarize it here. It just gives two curves. The Cn coefficient as a function of the side slip angle. And so we have one curve for alpha equals 0, and this is for the F-16 aircraft. So you see for angle of attack that is equal to 0, the slope is positive, so we have directional stability. But if we increase the angle of attack to 30 degrees, then we have a curve, so a yawing coefficient, Cn, that for most side slip angle has a negative slope, right? So here we have a negative slope. Therefore, for high angles of attack, we might lose directional stability. So is a aircraft always directionally statically stable? Not really. It depends on the angle of attack. Okay, so now we need to describe the next coefficient, Cn delta A. So it's the change in yawing moment due to a change in the aileron deflection. And this is a cross-control derivative because the ailerons are not the primary control surfaces to change the yaw of the aircraft. That is the rudder. That's why this is a cross-control derivative and not a primary control derivative. Now, for conventional ailerons, so just imagine, this aircraft over here. This is conventional aircraft with the ailerons that are placed near the tips of the wings. Then if we have a positive aileron deflection, which means that the left aileron has a trailing edge that goes down, and the right aileron has a trailing edge that goes up. So we're creating, since we're turning, so in other words, we're turning towards the right, that means that we're creating more lift on the left wing than on the right wing. But once again, more lift means more induced drag. So there's more drag on the left wing sorry, wrong perspective. So there's more drag on the left wing than on the right wing. So the resulting yawing moment is negative. Therefore, if we are using traditional ailerons, once we apply a positive aileron deflections, so therefore right wing down, we have a side effect of turning the nose towards the left. So right wing down implies nose to the left. And so this phenomenon is known as adverse yaw because the nose points in the other direction with respect to the direction that we want to go. Now, there's another way we can roll the airplane, and that is by using spoilers and not conventional ailerons. So spoilers are control surfaces that are on top of the wings, like in this case. And the way you generate a rolling moment is to deploy, so to deploy the spoiler on the wing that you're rolling into. So let's say you want to roll to the right, then you deploy the spoiler on the right wing. And what happens is that you decrease the lift on the right wing, so you start rolling towards the right. But by deploying the spoiler, you're also increasing quite dramatically the drag. And although you have decreased the lift, the lift-induced drag, although that decreases, but the drag created by the spoiler itself is much higher. Therefore, and now we have a different condition of causing a positive yawing moment as a result. So once again, let me describe this again. With the traditional ailerons, you have increased lift on the high wing and decreased lift on the lower wing. This change in lift causes an induced drag. So there's more induced drag on the upper wing than on the lower wing. So we are creating a negative yawing moment. So we have an adverse yaw. Instead, if we're using spoilers, so we're only raising the spoiler on the wing that we want to roll into. So let's say we want to roll to the right, we raise the right spoiler. That does two things. That decreases the lift of the right wing, and so it also decreases the induced drag, but the spoiler itself produces so much more drag than overall the drag on the right wing is higher than the drag on the left wing. Therefore, the resulting yawing moment is positive. This is a positive yawing moment. Therefore, we have a proverse yaw. In other words, if we are using spoilers, a right wing down means that the nose starts pointing to the right. As an example, the F4 incorporated both ailerons and spoilers to balance this side effect of adverse yaw. Now, finally, we have the last derivative, which is the change in yawing moment due to a rudder deflection. And this is the directional control power, or the rudder control power. In fact, the rudder is usually the primary control surface for producing yawing moments. Now, for conventional aircraft, we have the rudder that is mounted at the end of the vertical tail. So if we have a positive rudder deflection, which by convention means the rudder to the left, that causes, as we saw last time, a side force in the positive, along the positive y axis, and that creates a yawing moment in this direction, which is by convention negative. Therefore, Cn delta R is negative. Okay, so this concludes the description of all the coefficients. So now we know what they all mean. And here I created a little table with the summary of what we've seen so far in terms of the motion, the plane on which the motion takes place, then the trim condition for the particular motion, and the static stability condition. Well, here we can cancel this. All right, so starting with the longitudinal motion, that happens, that's sort of the pitching motion, so it happens along the xz plane. And the trim condition is Cm equals 0, with the static stability condition of Cm alpha that has to be negative. Now, for the lateral motion, well, the lateral motion is the rolling motion, so it takes place in the yz plane. Its trim condition is Cl equals 0, and the static stability condition is Cl beta less than 0. And today, finally, we concluded the description of all the static stability by describing the directional motion, which takes place on the xy plane. Its trim condition is Cn equals 0. And the static stability condition for a directional motion for the aircraft is that its derivative Cn beta has to be greater than 0. Now let's take a look at a numerical example. And this is example 5.3 in the chapter that I posted. So our task is to determine the aileron deflection and the rudder deflection in order to maintain a constant side slip equal of a beta equals 1 degree at Mach 0.9 at 20,000 feet for an F-15. And then the second task is to determine the side force coefficient Cy. So if we want to maintain a side slip, this is still a trim condition. It's just a constant side slip trim condition. So we still want Cl and Cn equals 0. But before applying that, well, here we have some more data. We have the 0 coefficients. They're all equal to 0 since the F-15 is symmetrical. And then we have all the derivatives. So let's take a look just at the derivatives and their sign to see if that makes sense. So let's check, first of all, the static stability coefficients. So let's take a look at the lateral one, which is Cl beta. So in order for the F-15 to be stable, this coefficient has to be negative, which it is. And for the directional stability, well, we need Cn beta to be positive, which it is. So the aircraft is stable for both lateral and directional motion. So now keep in mind that these coefficients are found for that particular Mach number. And also here, the angle of attack is not specified, but I assume that the angle of attack is a small one. The other thing that I want to take a look at is Cn delta A, which uh, gives us an idea when the ailerons are applied, whether we have an adverse or a proverse yaw. In this case, this coefficient is almost equal to 0, but is slightly positive. So we have a proverse yaw. That means is that when we are rolling to the right, also the nose of the aircraft tends to yaw towards the right. All right, so as I said, we still want a side slip trim condition. So we still want the overall external rolling moment and external yawing moment to be 0. So CL and CN has to be equal to 0. And we're imposing that beta is equal to 1. So this is slightly different from a level cruise condition in which there's no side slip angle. Here we want to sort of fly sideways. So because if we were at the level cruise, we already know the answer. If beta is 0, then also the control surfaces delta A and delta R, so the aileron and the rudder inputs would be 0. But now we want to fly sort of sideways a little bit, maintaining a constant beta equal 1 degree condition. So we have to apply some aileron deflection and also some rudder deflection. So that's what we want to compute. And in order to do so, we need to solve the two equations for the rolling moment coefficient and the yawing moment coefficient, and we just have to set them to 0 because that's what the trim condition implies. So now the only two unknowns that we have really are the control inputs, delta A, so the aileron deflection, and the rudder deflection, delta R. Everything else we know. So solving this simple two equation system, which is also a linear system, well, we find that the aileron deflection that we're looking for is 2.94 degrees, and the deflection of the rudder is equal to 2.4 degrees. That means that here we have the F-15 from the top. The rudder is angled to the left. Here you see two rudders because the F-15 has a double vertical tail. So we have a deflection of 2.4 degrees to the left, and a positive aileron angle. It means that the left aileron points downwards and the right one points upwards. And this is because we need to counteract the negative rolling moment generated by the aircraft's lateral stability. Because here we are, we have a positive beta angle. We have a positive side slip angle. So the lateral stability, since it's negative, is producing a negative rolling moment. So the aircraft would start rolling towards the left. And that is because it wants to cancel out the side slip angle by rolling towards the left. So if we want to maintain the side slip angle at a constant value, we need to enforce an opposite rolling moment. And that is done by controlling the ailerons. So we are creating a positive rolling moment to counteract the natural lateral stability of the aircraft. Now the second task is very simple. We just need to calculate Cy, and we know all the coefficients, and now we know also, well, the side slip angle and the aileron and rudder deflections. Here I'm Since all the coefficients are given in radians to the -1, we have to transform the angles, convert the angles from degrees to radians by multiplying by pi and divided by 180. The side force coefficient that we're finding is negative. So does that make sense? Yes, it does, because we have a positive side slip angle. So we have the relative wind that pushes on the right side of the plane. So we're expecting a side force pointing to the right, so to the negative direction in terms of the y body axis. So it is indeed correct that the value is negative. All right, so the last thing that I want to talk about is crosswind landings. So let's say that we want to land on a runway, but we have the relative wind is not aligned with the runway. So let's say that the runway is like this, but the relative wind comes from an angle. So we can decompose the relative wind vector v infinity into a forward component, which is our u component, and the crosswind direction, which is what we know as v. Now we have two approaches that can be done. So the first one is the motion that is known as crabbing into the wind. So you're approaching the runway sideways. So you maintain a coordinated wings level flight. So coordinated is a synonym for side slip angle equal to 0. So in other words, you're going you're pointing the nose of the aircraft in the direction of the relative wind. And then when you're close enough to touching down, you rotate the nose of the aircraft so that it aligns with the runway. So, and you see that very often if you've ever seen airplanes landing. If there's a little bit of crosswind, they tend to use this approach. The other approach is simply, well, you fly with your nose pointed in the direction of the runway, and so you have to fly with the non-zero side slip angle, like in the previous example. And so you'll have a positive side slip angle and probably also a positive roll angle. So what you need to do is when you're about to touch down, you just have to level the wings, and that's it. And so this is known as the trimmed side slip condition, which is actually the same that we saw in the previous example. So let's analyze this second case that is more interesting. So given the two components of the wind velocity relative to the aircraft, or the velocity of the aircraft relative to the wind, it's the same thing. So the side slip angle is the arctangent of the cross component v divided by the forward component u, or arc sine of the cross component v divided by the overall relative velocity v infinity. As we saw, we still require for trimmed flight to have both the rolling moment and the yawing moment coefficients to be equal to 0. And so pretty much we're solving the same equations that we solved in the previous example. And so given a particular side slip angle, as we saw, you can come up with the proper delta A and delta R um, as control inputs to maintain that side slip angle. But we can use these same equations to find the maximum amount of crosswind that we can manage, or that an airplane can manage. And this is because delta A and delta R have limits. So we can only deflect the ailerons and the rudder up to a certain angle, plus or minus, but it is usually limited. And so this is done as follows. Um, given the two equations for the trim condition, and assuming that CL0 and CN0 are just equal to 0, which is a very sensible assumption, then we're left with these two equations with we want to know what the maximum crosswind is. So in other words, what's the maximum side slip angle that the aircraft can travel at, given the control input limits. So step number one is just to set the maximum aileron deflection. So you put delta A equals to delta A max, and then solve the two equations. So you come up with a value for the rudder deflection and a value for the side slip angle. Now repeat the same thing, so solve the equation, but now you set the rudder deflection to its maximum value, and now compute the aileron deflection and the side slip angle. So generally beta 1 and beta 2 are going to be different. And now we have to take a look at delta R1 and delta A2, because if both of them are within the limit, so if both of them are less than their corresponding maximum deflection, then both beta angles are possible, and so you just have to take the maximum between beta 1 and beta 2, and that is the maximum side slip angle that the aircraft can withstand. But let's say that the rudder deflection that you found in step 1 is higher than the maximum allowed rudder deflection, then beta 1 is not a solution. So you're only gonna take beta 2 as your answer, in the assumption that the aileron deflection is below the maximum angular aileron deflection. Now the third case is that if instead delta A2 is higher than the limit, but the rudder deflection is below the limit, then the maximum side slip angle is the one that you computed in step 1. And once you have your beta max, then the crosswind, the maximum crosswind velocity that the aircraft can withstand is just given by V infinity times the sine of the maximum side slip angle. So this is going to be easier to see in an example. And so let's take a look at this. We have a relative wind of 100 knots, and this is for the T-37 aircraft. And we want to determine the crosswind limit, or the maximum crosswind velocity, given these coefficients, and given the fact that we have a maximum deflection of the rudder that is 20 degrees, so plus or minus 20 degrees, and the maximum deflection for the ailerons of plus or minus 15 degrees. So here we're setting up the trim conditions. So step number one, take the maximum value for the aileron deflection, which is 15 degrees. And therefore, the trim condition equations only have two unknowns. You have beta and you have delta R. And you solve and you see that beta 1 is 32.33 degrees. And the rudder deflection is 51.5 degrees. But 51.5 degrees is higher than the maximum allowed deflection for the rudder. So this is not a viable solution. So let's see instead, with step two, we take the rudder deflection and we equate it to its maximum value of 20 degrees. We substitute into the two trim equations. So now our unknowns are once again the side slip angle beta and now the aileron deflection. So solving these two linear equations, we find that the side slip angle is 12.55 degrees with an aileron deflection of 5.82, which is less than delta A max. So this is good. And this, have to reject the first one. So you see that the maximum side slip angle is the one given from step two of 12.55 degrees, obtained using an aileron deflection of 5.82 degrees and a rudder deflection of 20 degrees. Notice here that I haven't used the degree to radian conversion simply because the coefficients here, the derivatives, are already expressed in terms of 1 over degrees. So there's no need to convert the degrees into radians. All right, so finally, if we want the crosswind maximum velocity, we take our V infinity, which is 100 knots, and multiply it by the sine of the side slip angle, 12.55 in this case. So we find that the maximum allowed crosswind velocity is 21.73 knots. Of course, in real life, you want to stay below. This is the maximum theoretical crosswind. Probably in the manual of the plane, they would recommend not to exceed 15 knots. All right, so this is all for today, and I'll see you virtually next time. Take care.